Hey guys, this is Mr. Lowry. This is some notes that we took in class, some things we talked about in class on day one of the week of December 7th. So if you're in A cohort, this lesson would have been on December 7th, which is a Monday. If you're in B cohort, this lesson is for 12/8, which would be a Tuesday. We're talking about sequences again, and if you recall from last week, an arithmetic sequence is like a kind of like a linear sequence. We just don't say linear. We talked a little bit about how arithmetic sequences are very similar to linear functions, and I want to kind of continue that conversation a little bit, and this will help you with some of the questions on the homework for tonight. So this is what the homework for tonight looks like. It's arithmetic sequences part 2, and the first few questions are just asking us some kind of detailed questions about explicit formulas, linear functions, compare and contrast with explicit formulas, and this new thing we're going to talk about, which is called a recursive formula. So let's get started here. Right now, I have side by side a linear function and an arithmetic sequence. This function is kind of represented with this table right now, and this sequence is represented with this sequence. And what we want to do is we want to find out like kind of an equation basically for each one of them. So let's start with the linear function because this is what we're most familiar with. We see that this table here starts with 0. And when we're graphing a linear function, we often start with the y-intercept. So we'll, if we're graphing a function, we would typically start with a y-intercept, something like this, and then from there we would use the slope to find the next point, right? Something like that. Okay, so although there's some points over here on the left-hand side, typically our y-intercept is our starting point when we're making a graph. So this is like our starting point, 3. And you can see that this is the y-intercept because x is 0 and y is 3. So that would be, in a graph, that would be right here. So this is the y-intercept. Okay, now from there we see a pattern, right? The pattern is that we are adding 4 every time x increases by 1. So these are going up by 4, plus 4, plus 4, plus 4, plus 4. These are going up over here by 1, plus 1, plus 1, plus 1, and plus 1. Sorry, this is kind of some messy arrows here. That's the idea. So if you wanted to represent this, you could use like a slope-intercept form, basically. Y equals mx plus b, something like that. And we know that this is the slope, or the constant rate of change, and this is the y-intercept, or kind of our starting point. Now when we use function notation, we've been using f of x instead of y. Same kind of deal. From this table here, you can see that the constant rate of change is like 4 over 1, 4 over 1, 4 over 1. It's always 4. There's this add 4 pattern. So our linear function basically starts at 3, and then we add 4 times whatever x value we're at. So this would be 4x plus 3. So if x equals 5, for example, you would have 4 times 5, which would be 20, plus 3. So this would be 23. Okay? And you can kind of see that pattern, that plus 4 pattern. So if you start at 3 here, when x is 5, you've added 4 1, 2, 3, 4, 5 times. So f of 5 would be 4 times 5 plus 3. So you have a 4. There's 5 4s here when x equals 5. So that's kind of what our equation looks like. Now remember, this is the slope and this is the y-intercept. All right, let's take a look at the sequence, which is really similar. So notice that 3, 7, 11, 15, 19, 23, same kind of numbers over here, 3, 7, 11, and the pattern is the same. This is kind of like an add 4 pattern, add 4, add 4, add 4. Okay, now we might want to kind of pick some of these pieces here to work with. So what we know is that A1, the first term, is 3. And we also see that pattern, this guy right here, plus 4, that is called the common difference, and that's a 4. So first term, the common difference, and the letter we use there is D for difference. If we were to kind of take a look and see if we could find a pattern here. If you look at, like, let's say the sixth term, the sixth term, this is going to be 19 plus 4, which of course will be 23. But what I want you to notice here, something that's important, is that we don't have as many 4s, okay? If I'm looking at, let's say, term 5, for example, and you think about how many times you've added 4 at term 5, plus 4, plus 4, plus 4, plus 4, only 4 times. At term 5, you've only added 4 plus 4, you only added 4 5 times. Sorry, one more time. At term 5, you've only added 4 times. But over here in the table, when x is equal to 5, you've added 4 1, 2, 3, 4, 5 times. So the number of times you've added 4 over here is 1 less than the term number you're after. Okay, so let's look at step 6. This will be 23, right? When you're at term 6, you've added 4 1, 2, 3, 4, 5 times. It's 1 less. The reason why that happens is because here, notice that I'm starting at 1. So I have this 1, 3. Here I have 0, 3. The starting point for a function is the y-intercept, but the starting point for a sequence is the first term. Functions start at 0, sequences start at 1, and so we kind of see some funky stuff going on. So let's think about this for a second. If I wanted to find the 101st term of this sequence, how would that look? Well, I would start with 3, and then I would successively add a bunch of 4s. I would add a ton of 4s. But remember, if I'm sitting at term 101, then this needs to be 100. I'll have added 4 100 times, because the number of times I've added 4 is always 1 less than the term number, right? Let's look at that one more time. Term 7. How many times will I have added 4 at term 7? 1, 2, 3, 4, 5, 6. 1 less. Okay, so this would end up being 403, of course. But the pattern is this. If I want any term, an stands for any term in the sequence, kind of like f of x. I have to start with 3, and then I have to add 4 a bunch of times. Okay, but how many times I have to add it is 1 less than the term number I'm after. And so we represent that with an n minus 1. It all comes back to the fact that here in a sequence we start with 1, whereas here we start with a 0. Okay, let's compare again one more time just to kind of make sure that this makes sense. Let's look at x equals 3. Okay, at x equals 3, if I've started with 0, 3, I've added 4 1, 2, 3 times. And so the x number matches the number of 4s I have, right? 4 times 3 plus 3. Over here, though, if I look at term 3, first of all, here I'm at 15, here I'm at 11, right? Because here I started with 0 and then worked my way up. Here at step 3, I've only added 4 1, 2 times instead of 1, 2, 3 times. So the numbers, the x numbers, are basically shifted a little bit. They're a little bit off. This guy starts at 0, this guy starts at 1. So let's compare and contrast these, all right? Very similar ideas. Again, this is basically a linear function. So here's your slope, right? Here's your y-intercept, or your starting point. Over here you have those same numbers, right? Here is the d, the common difference. It's like basically your slope. It's like your constant rate of change. The fact that you're adding, 4 every time x increases over here, and here you're adding 4 every time your term number increases by 1. Okay, but here's your starting point, 3, right? Start at 3 on the y-axis, and here this is saying start with the number 3 for your first term. So you both have a 3 that you're, adding to. You have a 4 that you're multiplying something by. Okay, here the input variable is x, and here the input variable is n. But we have an n minus 1 right there. Because, again, the number of times you've added the common difference is 1 less than the term that you're after. Okay, so let's take a look at your homework really quick. Okay, explain why the explicit formula for an arithmetic series, sorry, this should say sequence. Sequence, excuse me, has an n minus 1 instead of just an n. Okay, it goes back to this idea. Now you'll put this in your own words, and you can even use an example. You can use this as an example if you want. But the idea is when you're adding the common difference a bunch of times, you've added it one less than the term number you're at. So if you want term 101, you've only added 4 100 times because we don't start adding until term 2. We don't add on term 1 because this starts at 1 and this starts at 0. So put that in your own words, but that's kind of the idea there. Okay, 2, compare and contrast a linear function with an explicit a linear function with an explicit formula for an arithmetic sequence. So we got a function compared with an arithmetic sequence, but we're talking specifically about the formula. We want to talk about the different pieces of each and how they relate, and how is a linear function equation different from the explicit formula for an arithmetic equation. Sorry, there's a few typos on this. I should say sequence again. Okay. So, if you go back here, let's talk about these really quick. This guy right here, we call an equation. Now, it's a function equation, so I would call this a linear function equation. Okay, now this guy right here, this is called an explicit formula. Okay, we don't really call it an equation, but that's the idea. It's basically an equation called an explicit formula. But it's not for a linear function, it's for an arithmetic sequence. Okay, so how do they compare? Well, they both have their own notation, right? F of x, a of n. They both have an input variable. This one's x, this one's n. They both use like a kind of a constant rate of change, common difference kind of idea. They both have a starting point. The difference here is the notation slightly different, the order slightly different. Also, this has a n minus 1 instead of just an n. And that goes back to sequences starting at position 1 instead of starting at position 0. So that's what's happening with this, excuse me, this function equation for a linear function and this explicit formula for an arithmetic sequence. They're very, very similar. They're just, pieces are in a little bit different spots, the notation's slightly different, and they start at different places. All right, the next thing we need to talk about is a recursive formula. Okay, so recursive means repeating, basically. And a recursive formula is a formula that relies on previous outputs. Okay, in this case, an output for a sequence would be like a term. Okay, so that's a recursive formula. It's kind of hard to see what that looks like, so we're going to kind of compare and contrast one more time and what a recursive formula looks like. Let's go ahead and start with a sequence. We'll do like a new sequence here. So let's do this guy. Oops. 16 and 19. So it's going up by 3 every time. Okay. So in this case, we would want to, if we were going to describe the sequence, this is kind of how we would describe it. First thing we might say is sequence starts at 7, right? Or the first term is 7. You also might describe what's happening. So if I were to ask you, okay, how are you going to find term 6? You might say, well, take term 5 and then add 3 to it, right? So you basically are going to say, take the one before it and add to it. So you would say something like this. To get a term, add 3 to the previous term. Okay? We're trying to represent this in words so that it will make sense when we represent it with a recursive formula. Okay? So let's take a look at a couple different steps and we can see if we can find a pattern. Okay? Let's take a look here at A6. So to get A6, how do you get A6? Well, you would take A5, this term, let's add some numbers here, term 1, term 2, term 3, term 4, term 5, term 6. To get A6, you would take term 5, and this is how we represent term 5, and I would add the common difference to it, which in this case is 3. Okay, cool. So that's actually going to give us 23, but what if we wanted to find A7? Okay, well, A7, we would take A6, which is 23, and we would add 3 to that, and that would give us 26. Okay, and to get to A8, we would take A7, 26, and we would add 3 to it, and that would give us 29. All right, so take a look at this and let's see if we can generalize it. What we're saying here is whatever term you want, you have to know the one before it and add 3 to it. That's called recursive. This is the recursive idea. It's using the previous output. It's using the previous number and adding to it. So this is saying, okay, take the answer from the previous guy, like the answer was 26, and add 3 to it, and you get 29. So A6, the answer is 23. Cool. Take 23 and add 3 to it to get A7. Take that and add 3 to it. You're constantly using the previous terms here. So let's just kind of generalize. Let's say you wanted any term, okay? Well, if you wanted any term, then you'd have to know the one before it. So if you wanted A100, you'd have to know A99. If you wanted A1001, you'd have to know A1000. So how we represent that is like this. We put an A with a n minus 1. Now in our explicit formula, we have n minus 1 as part of it, but we don't have A of n minus 1. So this here is really just a label that means 1 previous. It's just the term that's right before this one. So this is any term we want. This would be the one before it. And what we're going to do is we're going to take it and we're going to add 3 to it. That's the pattern here, right? So let's say this is like A100. Well, this would be A99 plus 3. If this was A1000, this would be A999 plus 3. It always relies on the term that's previous. Okay? This is a recursive formula. Now we actually need to add one more thing to make it complete, and that is the starting point. So notice that the way we described a sequence was its starting point and then its pattern. To get a term, add 3 to the previous term. That's what this is saying. To get a term, add 3 to the previous term. That's what this is saying in mathematical language. So we just need to now represent this in mathematical language. Sequence starts at 7. And so what we would do is do A1 equals 7. So this all together is our recursive formula for this sequence. Okay? So in general, for any arithmetic formula, this is what you need. A of n is equal to A of n minus 1 plus d, right? That's the common difference, that pattern number. And then you put a comma, and you put A1 equals blank. And all you're going to do, sorry, this is a comma, not a D1. You're going to replace the D with whatever D is, and you're going to replace this with whatever A1 is. Okay, let's get a little bit of practice with that so we can see what's going on, and also we'll do a little bit of compare and contrast with explicit. Okay. All right. So on the left here, we're going to do explicit formula. And on the right here, we are going to do recursive formula. Okay. Explicit formula, the input is the position number. We'll talk about that in a minute. So position number is input. Okay, for a recursive formula, it's a previous term is the input. Okay, let's put the kind of the template that we use. So for an explicit formula, you have an equals a1 plus n minus 1 times d. That's the template. For a recursive formula, you have an equals a with an n minus 1 plus d, and then you have a comma, and then you write a1 equals blank. Okay, now again, don't get tripped up by this one. A lot of students sometimes get tripped up by this. This is just a label, and it simply means the term before this one. Okay, notice this one has an n minus 1, and this is a with a little n minus 1. So the input here, this right here, this 1, this is a position number. So if you want like the 100th term, then this becomes 100. You subtract 1 and you get like 99 times d. Okay? Here, we don't use, like we don't plug in an n, we just grab the previous term. So let's actually get a sequence and see what's going to happen here. So I'm going to put this in the middle because this is going to be a sequence for both of them. So let's start with 4. And let's do, we'll add, let's say, 5 every time. So 4, 9, 14, and we'll do 19, 24, right, and so on. Okay, that's our sequence. Now, if we want to write an explicit formula, all we do is we replace the a1 and the d. For this sequence here, a1, the first term, is 4. And d, the common difference, or the pattern, the number that we're adding every single time, is 5, right? It's plus 5, plus 5, plus 5. Okay, so d is 5. So to write our explicit formula, we have an equals 5 plus n minus 1 times, oh, sorry, a1 is 4, not 5. Start over. Sorry, an equals the first term, which is 4, excuse me, plus n minus 1 times 5. And 5 is the common difference. All we have to do is use this template and replace that guy, and we got it. This is our explicit formula right here. Okay, now for our recursive, we do the exact same thing. It's a little bit different of a template. We just replace this guy, and then we fill in the blank here. So we got a1, and we got d. So the recursive formula looks like this. an equals a of n minus 1. Now again, this doesn't mean, we don't do anything. We don't replace anything here. We just bring it down. And then what we replace is the d. Okay, and then comma, a1 equals 4. Okay, this is a recursive formula. So explicit, recursive. Okay, that's how you get them. Now let's talk about like kind of what they mean again. Now remember, this is just more of like a statement of the pattern. What this is saying, for whatever term you want, you got to take the previous one and add 5 to it. So let's look at this guy real quick, and let's see if we can find a of 101 using our explicit formula. Okay, so that's the 101st term. What we would do is we would start with 4, the first term in the sequence, and the pattern is to add 5s, to keep adding a bunch of 5s, plus 5, plus 5, plus 5, plus 5, right? But at the 101st term, we'll only have added 5 100 times because we don't start adding 5 until the second term, which is why we have n minus 1 here. So we have 100 minus 1. Now a lot of times, excuse me, sorry, this is 101 minus 1. Okay, a lot of times students will just skip that writing step and they just know that this has to be 100. If this is 101, they'll just put 100 in there. But again, that n minus 1 is showing that this is 1 less than this guy. So altogether, the 101st term is 504, right? 500, 5 times 100 plus 4. Okay, so that's kind of nice. The explicit formula is nice for jumping way down the line to a specific term. Okay, now let's look at the recursive. If I wanted a of 101, what my recursive formula says to do is take a of 100 and add 5 to it. But we don't know what a of 100 is. So in order to get a of 100, I'd have to know a of 99, right? Every time I know a term, I have to know what's in the previous position, and I don't know that in this case. I don't know what a of 99 is. So the problem with the recursive formula is you can't jump to like a number way, way down the line. You can with explicit. So at this point, a lot of students were like, well, what's the point of recursive? Okay, recursive formula is really more of a way to build a sequence. This is instructions for building a sequence. So if you want to make that note to yourself. Okay, if you were like, okay, let's start with 4. So let's do this. Let's do a1 equals 4, okay? And then you're like, okay, well, what's a2? Well, our formula says a2, the second term, is equal to a1 plus 5. And since we know a1 is 4, we just go 4 plus 5, and that's equal to 9. Okay, so what's a3? Well, according to my formula, a3 is a2 plus 5. And since a2 was 9, it's 9 plus 5, which equals 14, right? And a3, and so on. And all this is saying is, you know, a4. If you want a4, you got to take a3 and add 4 to it. Or excuse me, add 5 to it. So that's 19. If you want a5, you got to take a4 and you got to add 4 to it. So, sorry, add 5 to it. I keep doing that. Got to add 5 to it. So it's 24. Okay, so if you're doing like computer programming, for example, or you're trying to give like instructions to a machine, recursive formula is used quite a bit in that because this is how a machine would sequence something. You can also tell it to like another mathematician. You're like, hey, this is how you build this sequence. You start with 4, or sorry, start with a1 equal 4, and to get every next term, you take the previous term and add 5 to it. All right. So start with 4, add a 5. To get the next one, add another 5. To get the next one, add another 5. To get the next one, add another 5. That's what this is saying. It's like instructions for like a machine or another mathematician to build up a sequence. It has some drawbacks, though, because you can't get to A100 unless you know A99. And you can't get to A99 until you know A98. Whereas the explicit formula, you can jump right there. Okay, let's look at a couple homework problems really quick and get you on your way. Okay, so for these problems here, 4, 5, 6, and 7, we need to write an explicit formula and a recursive formula. So let's write down the format for both of them just so we have it handy. Okay, so explicit, I'm going to do EF, or explicit formula. AN equals A1 plus N minus 1 times D. All we got to do is replace A1 and D. Okay, recursive formula. AN equals AN minus 1 plus D. This does not change. This does not change. We just change this part. But we also have one extra piece, and we say what A1 is. So in both cases, if we want to write a formula, we need to know A1 and we need to know D. So let's start there. Okay, for this number 4, we know that A1 is equal to 23. Okay, if we find the common difference, the pattern, it looks like we're adding 200 every single time. So D equals 200. Okay, explicit formula. We're taking this template and we're going to replace this and this. So AN equals A1, which is 23 in this case, plus N minus 1, that stays the same, times D, which would be 200 in this case. That's it. That's my explicit formula. Okay, let's write a recursive formula. AN equals AN minus 1. Remember, that doesn't change. Nothing changes here. What we add is the D. And again, this is not a D1. This is a comma for the second piece. So A of N minus 1 plus D, plus the common difference, plus 200. okay? Comma, or you can go down to the next line here, and then write what A1 equals. A1 is equal to 23. That's your recursive formula, okay? This is great if you wanted to jump down to like the 1,000th term or the 1,000,000th term. You just plug in 1,000,000 and you go from there. This is more of an instruction set for building a sequence that says start at 23, and then for every successive term, take the previous term and add 200. So for A2, take A1 and add 200. For A3, take A2 and add 200. For A4, take A3 and add 200, and so on and so on. Okay, let's look at some of these missing terms from the back here, okay? Now, the key here is that we know these are arithmetic sequences, so that's kind of important. So that means we're adding or subtracting the same number every time. So if we look at this sequence for a second, we realize that we are adding some number twice, okay? And that number is d. We just don't know what it is, but we do know what we're adding overall. So if you think about what does it take to get from negative 23 to negative 19, that's a plus 4, right? But what we're doing is we're adding d twice. So 4, the whole jump of 4, is equal to adding d 2 times. So what you have here is 2d equals 4, and you can solve that for d. If I'm adding 4 in 2 jumps, that's 2 for each jump. So this must be a plus 2, right? D equals 2. So if that's the case, if I add 2 to this, I'm going to have negative 21, and then I add 2 again, and I get negative 19, and that works. Okay, let's try a little bit harder one. Let's look at 16 for a second. Okay, so we're jumping all the way up from negative 34 to 26. What would that take? Well, if you wanted to know, you could find the difference, 26 minus negative 34, right? The minus minus becomes a plus, and this ends up being 60. So if I do negative 34 and I add 60 to it, that's going to get me to 26. But here's the problem. I'm doing it in 1, 2, 3 steps. So we have to divide 60 by 3. That means every time I'm adding 20, 20, 20. So we can get those terms. If you want to set up an equation like I did before, you could say that 60, this big jump, has to equal 3 times d, right? So there's 3 jumps here. That's like plus d, plus d, plus d, plus the common, remember d is the common difference. So if you divide both sides by 3, you get d equals 20, right? Same kind of idea. You're jumping by 20, which makes this guy negative 14, and this guy 6, and if I add 20, I should get 26, which kind of makes sense. Okay, one more. Okay, here I got 4 jumps that's happening. Okay, so that's 4d, plus d, plus d, plus d, plus d. Right, now we got to figure out what's going on here. And that to me looks like it's going down by, looks like 24. So again, if you're not sure what's happening here, you can subtract. Negative 31 minus negative 7. Right? This is like a y2 minus y1. You just figure out what's happening there. So negative 31 plus 7, that's going to be a negative 24. So this whole thing is going down 24 all the way down here. And again, we get there by subtracting. So if you want to know, what that jump is, negative 23 minus negative 31 will tell you what you're increasing by. Negative 82 minus negative 22 will tell you what's going on from here to here. So negative 31 minus negative 7 is a negative 24. That means from here to here, I'm going down 24. But I'm doing it in increments of, I'm doing it in 4 increments, right? So this is like plus d, plus d, plus d. So negative 24 equals 4d, or take negative 24 and divide it by 4, and you get the difference. The common difference is negative 6. So I'm going down by 6 every time. So negative 7 minus 6, that's negative 13. Okay, minus 6 again, that would be negative 19. right? Minus 6 again, that's going to be negative 25. And if you minus 6 again, it should get you to negative 31, right? Which makes sense, okay? So use the fact that it's arithmetic and that you're adding the same number every time, and then figure out how many jumps you have. Okay, if you have 1, 2, 3, 4 jumps, you got to take whatever this big jump is and divide it into 4 equal pieces so you can make that jump. Okay. Some of these are a little tricky because the negatives, so you may want to start on, the ones that kind of have like positive numbers, but the idea is kind of the same. So that should help you get going on those problems. So finish that up, and this will be due on the end of day 2. So depending on what cohort, and that might be a different day. All right, hope that helps, and I'll hopefully talk to you soon. Thanks.